All right. The practice exam. Now, there have been concerns raised in the past that these practice exams were always too easy. And people were saying, you know, the practice exams are so easy, and then we go take the exams, and the exams are like crazy hard. So we said, you know what? We're going to change that. We're going to make the practice exam crazy hard. And that way when you get to the exam, you'll be like, well, at least it wasn't the practice exam. So this is a non-trivial practice exam. And I hold out hopes that we can finish it in 45 minutes. And let's find out. So here we go. Question number 1. Find the third-order Taylor polynomial centered at x equals pi for the function f of x equals e to the sine x. Now, the phrase third-order Taylor polynomial can also be written as P3 of x. So they might say find P3 of x. But what is the third-order Taylor polynomial? Well, essentially it's like the Taylor series, but you just don't keep going. You just stop after 3 terms. Now, we have ways to find Taylor series without actually taking derivatives, and that is we use existing Taylor series. The problem is we can't do that here because we don't have like e to a polynomial, we have e to the sine of x. So we don't have a clean way to say, oh, let's just take what we already know and adapt it. But that's okay. Even if we can't do that, we still always have the definition. So P3 of x means what? Well, it says if you have your function, it's going to be f at your center. So pay attention to where your center is. Most of the time we've done your center at 0. It doesn't have to be. In this case, the center is at pi. So f of pi plus f prime of pi times x minus pi plus f double prime of pi x minus pi quantity squared over 2 plus f triple prime of pi x minus pi quantity cubed over 3 with a little factorial. So I can put 2 little factorial. 3 factorial, also known as 6. So the center shows up in 2 places. It's where you evaluate your derivatives and you have your x minus terms. And so that's where you want to have it go. So really, when you have to find a third-order Taylor polynomial or second-order Taylor polynomial or whatever order Taylor polynomial, there's testing on a couple of things. The first thing is, do you know what we're looking for? And then the next thing is, can you actually do it? Which means, can we take our derivatives? So we start with f of x, e to the sine x, f prime of x. Anyone know that? Yeah, e sine x and chain rule, cosine x. This is like cool times. Reminds you of when you were young and innocent and you were taking Calc 1. And you're like, Calc 1 is so much fun because it's just derivatives. What could be hard? So there's f double prime. You use the product rule. When you take the derivative of e to the sine x, the letter cosine comes down. That's where the cosine squared x came from. E to the sine x, the derivative of cosine is negative sine. And this one, it's a little bit messy when you get to the third derivative. And in some sense, this almost tests your patience. But that's okay. We have almost infinite patience. We're in Calc 2. We're pretty good at that now. So you just go through and carefully work through your derivatives one layer at a time. Product rule, chain rule, whatever you need. And let's see, the last one, b plus e to the sine x minus cosine x. All right. So I'm not going to spend too much time dwelling on these derivatives, but it's the derivatives that you would get. Just be patient. Be patient. Now, like I said, this one is crazy hard. Odds are pretty good if we give you a function, it's not going to have a derivative quite this adorable. All right. Now, these are not what get plugged into there. Because remember, you have to evaluate. Okay, well that's good news, because when we evaluate, things should simplify. So, what we do is we plug in pi into every one of these terms. All right. So to help us, we just need to remember a few things. One thing to remember is that sine of pi is 0, and cosine of pi, do you remember that one?
1.
Negative 1. All right. So, everywhere you see sine, that's going to become 0. Everywhere you see the cosine, that becomes negative 1. So e to the 0 is 1. E to the 0 times negative 1, negative 1. E to the 0, negative 1 squared, so that's 1. E to the 0 times 0, so that's 1. Okay, this one will take a second. E to the 0 is 1. Negative 1 cubed, so this is going to be negative 1. Next term will be 0 because of the sign. Next term will be 0 because of the sign. The last one, e to the 0, minus minus 1. So makes plus 1, minus 1, plus 1, 0. Okay. So, our answer, now we just plug in these values. F of pi, 1. F prime of pi, minus 1. So, 1 minus x minus pi. F double prime of pi is plus 1. And 2 factorial, make that a half. X minus pi, quantity squared. F triple prime of pi, 0. Don't put anything. There you go. And so, this is our third order Taylor polynomial. Now you might notice, wait, but it's not a third degree polynomial. Look, third order doesn't refer to what's the degree of your Taylor polynomial. What it refers to is how many derivatives did you go up to. And if your last derivative was 0, it may not be the same as your degree. Now, you might ask the question, shouldn't we expand? And the answer is no. Don't do that. There's good reasons not to do that. 1, you're likely to make a mistake. But 2, it makes it harder to grade. And you don't want to do that to your grader. You want your grader to be happy. But really, the real reason you don't want to expand is in terms of practical application, you want it written in this format, x minus a, because that's how we like to think of these things. All right, any questions on number 1? Okay, good. Number 2. Determine if the following sums are absolutely convergent, conditionally convergent, or divergent. Now, for full points, include the name of the test if I use any test. Okay. Now, if I don't want full points, I can skip the name of the test. But remember, got to get them all. Do the work. Follow the instructions. If a problem says, you don't have to justify your answer, don't justify your answer. On the other hand, if a problem says, you have to justify your answer, you should justify it. Pay attention. Pay attention. Okay. So, I guess we'll go through these in order. Don't worry, I have spare paper. I don't think we're going to be able to fit it all on this one sheet. Okay, A. The sum, k equals 100 to infinity, negative 1 to the k, over k log k, log k, log k, to the 1/2. All right. Now you probably said, wow, why don't you keep going? Then you could have said log. And that's for next semester. You know, every semester we add an extra layer. All right. So, well, let's see. First off, can we say anything about whether this converges? Yes. See this minus 1 to the k? Whenever you see something that is minus 1 to the k, sometimes we like to hide it. How do we like to hide minus 1 to the k? Cosine pi n. That's a hidden minus 1 to the k. We don't have very many tricks, so I don't mind revealing them to you. You're my best friends now.
Is there any other way to write negative 1 to the k?
Probably. But in terms of what we have, that's pretty much the 2. Okay. So this alternates. Now, does the bottom go to infinity? Or in other words, does the terms go to 0? Yes. Yes. Okay, if alternates goes to 0, you're done. Now, technically, there's more to show for the alternating series test, but we just trust you. If you see that it's alternating and going to 0, we're going to give it to you, because these functions are all really reasonable functions. So, alternating series test. This converges.
So we don't have to prove the alternating series test?
Well, you have to say it's alternating and goes to 0. Alternates goes to 0. Say it's alternates and goes to 0.
But you don't have to like write a whole bunch to prove that it decreases to 0.
No, we're not asking that.
All right.
Okay. So, am I done?
No.
No. Because I've shown it converges, but there's two kinds of convergence, the absolute and the conditional. Okay, so now I have to go deeper. Deeper, deeper. How do I go deeper? Well, the answer will not surprise you. I get rid of the minus 1 of the k. So conditional says, drop the alternating part, does it still converge? So we now look at the following sum. K equals 100 to infinity, 1 over k log k log k log k to the 1/2. And now the question is, does this converge or diverge? Okay, first off, never worry when you have questions about convergence, never worry about where you start your sum. The fact you start at 100 doesn't matter. What matters? The tail, the infinity part. Okay, so let's start thinking about tests. What test? The integral test. The integral test. All right. Well, why? Well, essentially, this is really close to 1 over k. It's right on the edge. 1 over k just barely fails. So we do the integral test. 100 to infinity, 1 over x log x log x log x to the 1/2 dx. Can we integrate this? Well, the answer is, I hope so. Otherwise, it's a terrible test. And it's okay to try a test and say, well, that's not working. Let me try a different test. If you stare at this for a while, you say, this log at the end is inside a 1/2. Well, let's call that u. U is log x du. Well, this is an onion problem. You got layers. There's layers. You got to work through it. And it's okay. You can cry a few tears. You're going to say, it's just, I have a cold coming on. Okay. Log outside, so it's 1 over log. Then times the root of log. Well, that's 1 over log times the root of log, which is 1 over x. Which means that's du. So this becomes the integral of something, I don't really care, to infinity of 1 over u to the 1/2, or u to the minus 1/2 du. Well, that's not a bad integral. That's 2 u to the 1/2 from something to infinity. Well, what happens to that? It goes to infinity. So this diverges by integral test. So if the original sum converges by alternating series test, when we drop the alternating, it diverges. What kind of thing can we say about A? Conditional. Conditional. All right, so that's part A. Now, for part B, well, we have this expression. 1 plus root n, 2n plus 1, 1/2 n plus 1, square root of n plus 2. Okay. Now, whenever you see something like this, you see all those plus signs? Plus signs are like, there's stuff I can ignore. And you say, I just am only going to focus on the most important thing. And when I say the most important thing, what do I mean by the most important? Whatever grows fastest. So everywhere when I see plus signs, I'm going to say, let me just throw away the thing that's small, keep the thing that's big. That's going to help me understand how it's growing. Next thing, notice the terms here, there's no negatives. Can I be conditional? If you don't see a negative, it cannot be conditional. It's either absolutely convergent or it's divergent. So we know now it's one of those two, absolute or divergent. Okay.
How do you prove that when you're writing it on the test?
Prove what?
That it's not conditional because there's no negative signs.
That's the definition of conditional.
Okay.
Conditional says you depend on the negatives. If there's no negatives, you can't be conditional.
All right, so you don't have to write that down. You can just say absolutely convergent or divergent?
Yes.
Okay.
So, let's go through this. All right, again, I don't care that I start at 50. On the top, inside the square root, what matters, 1 or the root n? The root n. So I really have on the top root n, which is really n to the 1/4. So I'm trying to get a handle on what the growth is. So upstairs, it's n to the 1/4. Downstairs, the 2n or the 1. Which one matters? The 2n. And the 2 doesn't matter because it's a number. So really, the first term grows like n. The second term, 1/2 to the n or 1. Which one matters? The 1. Exponential growth also can be exponential decay. What happens to 1/2 to the n as n goes to infinity? Goes to 0. And 1 beats 0. Okay, last term, square root of n plus 2. Well, inside the square root, what term matters? The n. So it's really square root of n, or n to the 1/2, which tells us, well, if I clean this up, this becomes n to the 3/2 downstairs with an n to 1/4 upstairs. So it becomes 1 over n to what power? 5/4.
So the first n on the bottom should be like 2n?
The 2 doesn't matter. Because I'm trying to figure out how things grow. And so growing is like, changing. The 2 is sort of fixed. So if I'm just trying to do growth, I could put the 2 there, but it doesn't really help me decide how things are growing. So the moral is, really this is growing like n to the 5/4. Okay, so does n to the 5/4, let's think about that sum. The sum, n equals 50 to 100 of n to the 5, sorry, not 100, infinity. N equals 50 to infinity of 1 over n to the 5/4. Does that converge or diverge, and why? Converge because? P series. So we now suspect, in fact, we more than suspect, we know what's going to happen to this sum. It's going to be convergent, it's going to be absolute. Because we know what it grows like. But we still have to justify it with a test. What kind of test do we want to use? Either a limit comparison or a comparison. If you do a limit comparison, what do you do a limit comparison with? You do a limit comparison with this thing. Because then you can really break it up into pieces. This n to 1/4 goes into that part. This n goes into that part. That 1 goes there. N to 1/2 goes there. And you say, how does each piece converge? But I'm in a different kind of mood today. So I'm going to do comparison. Because I like comparison.
What test were you using when you got rid of all the plus signs in the first part?
Well, I wasn't doing any tests. I was trying to understand growth.
Okay.
But really, when you do that, you're doing limit comparison. You're just not doing the technical terms. So comparison says what? Well, if I'm doing a comparison, I want to show it converges, I have to do what? Do I have to get something beneath it or something above it? I have to get something above which converges. So here's what I'm going to do. I'm going to get something above it, which is bigger, which converges. And all I have to do to get something above it which is bigger is just remember that to make a term smaller, I make the denominator larger. To make a term smaller, I make the numerator smaller. Okay, so let's work on the denominator. So what's something comparable to 2n plus 1, but smaller than 2n plus 1? 2n. Or even n. What's something smaller than 1/2 to the n plus 1? The 1. And again, the goal is get rid of the small stuff. Get rid of the unimportant stuff. What's something smaller than square root of n plus 2? Square root of n. Okay, now I have to get something bigger than square root of 1 plus square root of n. So I can't just say square root of n. Well, here's what I can do is I just go through and say, look, this piece right here, I'll replace it by the bigger piece. So downstairs what you do is you throw away the small part. Upstairs is you just replicate the big part. And that way you're going to guaranteed to get something which works. So this becomes, upstairs you get square root of 2 n to the 1/4. Downstairs you get 2 n to the 3/2. The 1 over square root of 2 times 1 over n to the 5/4. And now, same thing, this is a p series. You don't need to worry about the 1 over root 2. That's a constant. Constants, don't worry. So, by comparison test, it converges. And because there's no negatives, it's an absolute. All right? Okay, these are the easy ones. Let's do a good challenging one. You ready? This should get you excited for the test. It's like, man, I wonder what they came up with for the test. All right. So, the sum, L equals 1 to infinity, L to the power 4L, divided by 2L times L factorial over 3L factorial. And for some reason it says e to the fourth is approximately 54.59. I don't know why they said that. Who knows? Just a random fact they threw in. Okay. So, what test are we forced to use here? Ratio. And how do we know we're forced to use it? Factorials. Absolutely. There's no choice. It was forced upon us. Can this be conditional? It cannot be conditional. Why can't it be conditional? There's no negatives. If all the terms are positive, it's absolute or it's divergent. That's it. It's one of those two things. All right, so we're going to take a limit. N goes to infinity. And if you don't like, by the way, writing L's, you can change it to whatever script you like. I don't know why I wrote N. A sub L plus 1 over A sub L. And we've got to figure out what this number is. And then once we figure out that number, we figure out whether or not it converges or diverges. Or whether we have to do a different test. Hopefully we don't have to do a different test because we don't have a different test to use. Now the hardest part about the ratio test is getting that A sub L plus 1. More people lose points on problems like this at this step because they don't know how to replace all the L's with the L plus 1s. Here's how you do it. You replace all the L's by L plus 1. So that's the secret. And remember that. Okay, so what do I mean? Here, parentheses are your friend. So L becomes L plus 1 to the 4 times L plus 1 divided by 2 to the L plus 1. Go ahead, keep using parentheses. L plus 1 factorial 3 times L plus 1 factorial. Okay, that was the hard part. Good. The rest of this will be easy. Now, the A sub L, just flip it upside down. 2 to the L, L factorial, 3L factorial, divided by L to the 4 to the L. All right. Well, that was not so bad. What comes next? Equals. Now, we're going to find out if we can fit this all on the one line. All right. So this is L plus 1 to the 4L plus 4. So I'm going to break off 4 of the L plus 1s, and I also have L plus 1 to the 4L. So I'm breaking this into two parts. So breaking off, because I want the 4L to match that 4L. I want these exponents to match. The 2 to the L stays alone, the L factorial stays alone, the 3L factorial stays alone. In fact, really, the original term stays alone. The idea is to come to your L plus 1 and try to mimic the L things as much as possible. Pull terms off if you can. So 2 to the L plus 1, well, that's going to become 2 to the L times 2. L plus 1 factorial, what do you do there?
L plus 1 L factorial.
Yeah, it's L plus 1 L factorial. So the idea is you're pulling off the first term. The next term is 3L plus 3 factorial. How many terms are you going to pull off there? 3 of them. 3L plus 3, 3L plus 2, 3L plus 1, 3L factorial. And then, don't forget, you also still have L to the 4L. All right. Well, now, if you've done your job correctly, fingers crossed, what will happen? Cancellation. The exponentials will cancel, the factorials will cancel. And so that's good. We've got cancellation. Well, not everything cancels. Well, we can do a little bit more. We have an L plus 1 here. So I can cancel and get 3 of them. If we wanted to, we can even come here. That 3L plus 3 is really 3 times L plus 1. Then I can cancel off another L plus 1 because why not? I'm in the mood. And so what do we have?
You cancel off the L for 4L.
Well, these don't cancel. Because one of them is L plus 1 and one of them is L. But something will happen. And it'll be beautiful. Beautiful. All right. L plus 1 squared. Okay, let's see what we have downstairs. We have a 2 times a 3 makes 6. 3 times L plus 2. 3 times L plus 1. Now these are essentially all the polynomial terms. So I'm just going to group those together. And what we haven't grabbed yet are these terms. Now notice that they're both to the same power of 4L. Okay, that's cool. So it's something to the 4L, which you can also write as something L to the 4. So it's something to the L to the 4. Well, what goes inside here? Well, it is L plus L over L, which becomes that. Okay, I skipped 1 or 2 steps. I'm sort of smashing things together here, but that is what it does. Okay, now you might say, why have you painfully written things in this way? Because things are about to happen. Good things are about to happen because we're good people. Okay, these are polynomials. What degree polynomials do we have? Yeah, they're both degree 2. Now, you can, if you like, just divide both sides, top and bottom, by L squared. Take the limit. Or at this point, we trust you. You're trustworthy people. Just say leading coefficients. That's where it's going to go to. So what are the leading coefficients? Upstairs is 1. Downstairs, 54. Because I have 6 times 3 times 3. All right. 1 plus 1 over L to the L. L goes to infinity. What does that go to? E. That one you should know. Because we've done it like 4 times. So it goes to e to the 4. So the limit is e to the 4th over 54. Now, if you had a calculator, we'd be in good shape because we could compute e to the 4th. But we don't have a calculator. Oh, it's like they anticipated we'd need to know something. This is 54.59 over 54, which is about 1.01. So, converge or diverge? Diverge. Barely diverges. If this had been like 2.03 instead of 2, it would have converged. That's how close we are to converging. This is just barely across the line. So, limit of a sub L plus 1 over a sub L is above 1, so diverges, because I want all the imaginary points on this practice test. And you want all the real points on the real test. So remember to justify it. So that it diverges by ratio test. Okay, well that was good. 2 problems down, and we've taken up 30 of our 45 minutes. That's not a good sign. Let's go faster. All right. So find the center and radius of convergence. Now notice here it specifies center and radius. We'll come back to that in just a moment. All right. So what test do I need to start here to help me find the center and radius? Root test. And what's the clue? Everything has powers involved. Now, before I get too far down the root test, this n squared minus 25 over n squared plus 5n, that seems really messy. Can we find another way to write this? In factor. So it's like n minus 5, n plus 5 upstairs. What is it downstairs? And an n plus 5. Oh! They were messing with us. So really, the inside is n minus 5 over n, or 1 minus 5 over n. So let's take our root test. So limit n goes to infinity, absolute value of a n to the 1 over n. Well, okay, so that's the limit as n goes to infinity. This is going to become 1 minus 5 over n to the n squared to the 1 over n, whatever that does. And then I'm going to have 2x plus 5 absolute value, because we're taking the absolute value base of n. This could be negative, to the 3nth power to the 1 over n. Now, if you take the 1 over nth powers, you see that thing simplified fairly nicely. 1 minus 5 over n to the n. And this becomes absolute value of 2x plus 5 cubed. So let's talk about each piece here. The first piece, what does this go to? E to the negative 5. So minus 5, that becomes e to the negative 5. And what does 2x plus 5 absolute value to the third power go to? 2x plus 5 to the third power, because there's no n. Okay, so that's the limit, and that needs to be less than 1. Okay, so what do we do next? Well, we start moving stuff around. So this becomes 2x plus 5 cubed less than e to the 5th. I want to get rid of that cube. Well, to do that, I will employ the cubed root. So 2x plus 5 is less than e to the 5 thirds. So I take the cubed root of both sides. Cubed root of e to the 5th is e to the 5 thirds. Now I'm almost there, because what do I want to get to? I want to get to absolute value of x minus a less than r. This r is the radius. This a is the center. I'm practically there, but what's missing? Or what's there that shouldn't be there? The 2. So divide by 2. And the 2 can come out of the absolute value. So I get x plus 5 halves should be less than 1/2 e to the 5 thirds. Or x minus 5 halves should be less than 1/2 e to the 5 thirds. And now I read off my answer. Center, negative 5 halves. Radius, 1/2 e to the 5 thirds. And that one's done. Whew. I hope you have one like that on the test. Now, what do I do with the endpoints? Nothing! Why? Because it didn't say do anything with the endpoints. So if it says just find the center and the radius, just find the center and the radius. If it says find the interval, what do? Find the interval. You check the endpoints. Don't do more work than you need to, but do the work that you need to. I guess it's do the right amount of work. Do the right amount of work. All right. So given that 1 over x is equal to the sum k equals 0 to infinity of negative 1 to the k, x minus 1 to the k, find the exact value of the sum from k equals 0 to infinity, 1 over 2 to the k times k plus 1 times k plus 2. This is good. Now, you might say, that does not look like that at all. And you're right. Not yet. So now we're going to think about how can we make things look like that. So here's our sort of like we're going to put on our hat. Probably we want to use what we're given, because otherwise they wouldn't have given it to us. We have to believe that there's some good faith going on here. They're going to give us things that we find useful. So I'm going to absolutely believe that that 1 over x equals that sum is something which is useful. So now I want to think about what are things I can do to my series to manipulate it and rewrite it. In particular, I see that I have terms downstairs. When it comes to series, there are 2 tools we have that we can do, which are calculus tools. Take derivatives, take integrals. When we take derivatives, it introduces terms. Where do those terms end up? They end up in the numerator. They end up on the top, because you bring the powers down. When you take integrals, where do you introduce terms? In the denominator, because you divide by that new power. Are we going to need to take derivatives or integrals if I want to have stuff downstairs? Integrals. So the fact that I see stuff downstairs is sort of like a take an integral. Take an integral. In fact, it's not even saying take an integral. What is it telling me to do? Take 2 integrals. Oh, this is good stuff. Okay, so let's start with this. Let's take an integral. Don't worry about the 2 to the k. The 2 to the k doesn't really help us much because that 2 to the k, that's going to be handled here by this stuff. So I'll worry about that later on. Anything to the kth power I worry about later on. But it's that those polynomial terms, I have to bring those in. So I integrate antiderivative of 1 over x, natural log x. And when you take an antiderivative of a series, you just do it term-wise. So sum 0 to infinity, negative 1 to the k, x minus 1 to the k plus 1, divided by k plus 1 plus c. What should c be? Well, to figure it out, plug in a point. But which point? Plug in 1. Why? Because we're centered at 1. Plug in 1, you get 0 for your sum. Log of 1 is 0. So this is, in fact, just 0. Okay, that's cool. Cool. Now, what's next? Integrate again. See how this was cool? We already got the k plus 1. And we're like, hey, if you did this again, the next term would be a k plus 2, because you'd add 1. So the integral of log x, do you remember that? We did it before. Anyone remember? It's x log x minus x. Ah, good, you do remember. I was worried you'd forgotten. Now, if you're trying to say, how do you get that? The answer is integration by parts. And you might say, wait, I have to remember integration by parts? Well, you have to remember easy integration by parts. You definitely need to know it 2 weeks from now. In fact, 2 weeks from, is it today? I think it is 2 weeks from today. Oh, good times. Good times. Plus c. Now, what should c be? Well, what do? Plug in 1. Again, the sum drops out. 1 times log of 1 is 0. But then you have minus 1, which means this is minus 1. Or, using my fancy paper technology, I add 1. Okay, so now I have my sum. I'm practically done. It's amazing how close I am to being done. I'm not done, but I'm practically done because I've got the k plus 1. I've got the k plus 2. I just need to get that 1 over 2 to the k. So now, this is the, you must choose. But you must choose wisely. For the correct choice of x will bring you closer to the answer, but the wrong choice of x will take you further from it. So, what is a good choice for x? Well, 1 would be a terrible choice. Wait, what was it? 1/2. Let's try 1/2. Let's see what happens. So we plug in a half. So if you plug in a half, you plug it on both sides. So you get 1 plus 1/2 log of a half minus a half. Sum k equals 0 to infinity minus 1 to the k. 1/2 minus 1 is negative 1/2 to the k plus 2 over k plus 1 times k plus 2. Well, this is the sum k equals 0 to infinity. Because we chose a half, we have a lot of minuses. In fact, we have so many minuses, what happens to the minuses? They cancel out. Oh, sweet. Good times, good times. Okay. Then you have this 2 to the k plus 2, which is really close to 2 to the k. It's just you have another 2 2's. All right. Well, so now we're to that. We were so close. We almost made it. You have that 2 squared. Those 2 extra 2's. What do? It is a constant. And so we multiply and bring it across. Aha! And so, multiplying both sides by 4. You get the sum from 0 to infinity. 1 over 2 to the k plus 1 times k plus 2 will be equal to whatever this is times 4. 1 minus a half is 2. Sorry, 1 minus a half is a half times 4 is 2. 4 times a half is 2 log a half. And there's the answer. Ah, good times, good times. Okay. The following function is infinitely differentiable at x equals 0. In other words, we can find any derivative at 0 we want. So let's find the 30th derivative at 0. This sounds like a Calc 1 problem until you realize that you have to start taking derivatives, and you're like, no, I'm not taking 30 derivatives of this because I'm going to have to get a couple of reams of paper to write it all down. And I'm going to make mistakes, and I'm going to lose points. And then I won't have time to do all the other fun problems that were on this test. Okay, so we want to find the 30th derivative at 0. So what we do is we say, hey, this is kind of a red herring. Let's think about what the power series is. So focus on this. If you don't like the word power series, just think Taylor series. So I'm going to take this and rewrite this as 1 over x cubed sine of x cubed. And I say, I know the Taylor series for x cubed. So I'm going to take the Taylor series for x cubed. Sorry, Taylor series for sine. Taylor series for sine, which is the sum, 0 to infinity, negative 1 to the k, whatever is on the inside to the k, so that's x cubed, sorry, not to the k, to the 2k plus 1, and divided by 2k plus 1 factorial. Okay, so I took my sine of x cubed and turned it, because of what I know about sine of z, I was able to get the series. Take the 1 over x cubed in. So our series for f of x is the sum from 0 to infinity, negative 1 to the k, x to the, if we work our way through here, we have x cubed to the 2k plus 1. That's x to the 6k plus 3. But then I have this 1 over x cubed downstairs, 6k plus 3, but minus 3 gets me to 6k. Man, am I trying to think too hard. Divided by 2k plus 1 factorial. All right. So there we go. That's really what f of x is as a power series. But wait! F of x is also the following. It's the sum, 0 to infinity, of the nth derivative at 0, x to the n over n factorial. These are the same. They match. Now I say, well, if they're the same, all I have to do is figure out what piece I need to look at. I need to look at the part which would have the 30th derivative at 0. So look at the coefficient of x to the 30th. So if I look at the coefficient of x to the 30th, for the sum here, that would be the 30th derivative at 0 times 1 over 30 factorial, because that's n equals 30. Upstairs, when am I going to have x to the 30th? K equals 5. So I'm going to get negative 1 to the 5th, which is negative 1. And then I'm going to have 1 over 11 factorial. So rearrange. The 30th derivative at 0 is equal to negative 30 factorial over 11 factorial. And that was a lot faster than taking 30 derivatives. And did not take many reams of paper. All right. Number 6. Whew, I didn't think I'd see number 6. But we got here and we still have time enough to do a few problems. So find the Taylor series for the following around x equals 0. The first one is just a straight up, take your knowledge, 5x cubed. I know the Taylor series for e, it's the following. You take the sum, 0 to infinity, whatever's on the inside, x cubed to the kth power divided by k factorial. And then I can just bring that 5x squared inside. So that's the sum k equals 0 to infinity, 5, x to the 3k plus 2, because I have 3k from the x cubed to the k plus 2 more from the x squared, divided by k factorial, and part A is done. So that's part A. Yes, sometimes we do ask you easy questions. Now, let's skip to part C because I like part C. Part B is not too bad. Part C. Find this. Now this looks like it's complicated, like it's going to take us a very long time to solve it. Because you have to somehow take information about sine. You have to multiply that by 2x. Then you have 2 minus x squared cosine x. There's all sorts of shifting involved. You've got to get things lined up just right. But maybe there's a better way. There's a question, philosophically. What is h prime of x? Well, since it asks, let's go ahead and take the derivative. So we take the product rule. That's 2 sine x plus 2x cosine x plus negative 2x cosine x plus 2 minus x squared times negative sine x. And if you go through here and you stare at it and you say, you know, there's a couple of interesting things happening. Things cancel off. And when you're done, what you're left with is you're left with x squared sine of x. So the derivative is actually really simple. So what do? Well, if h prime of x is x squared sine of x, I say, well, that's x squared times the sum, 0 to infinity, negative 1 to the k, x to the 2k plus 1 over 2k plus 1 factorial, because we memorized the Taylor series for sine and for cosine and e to the z, geometric, all the good ones. We have those memorized. 0 to infinity, negative 1 to the k, x to 2k plus 3 over 2k plus 1 factorial. The 2k plus 3 came from multiplying the x squared in. Now, is this the right series? No, that's the series for the derivative. We don't want the series for the derivative. We want the series for the original function. So how do you get that? Antiderive. So h of x, sum, k equals 0 to infinity, negative 1 to the k, x to the 2k plus 4, 2k plus 1 factorial, 2k plus 4. Is that the right answer? Yep. No, because what have we forgotten? Plus c. And what is c? Well, how do you find c? Plug in 0. That goes away, that's 0. So we get c. But if I come up here and plug in 0, I get 0, 2 times 1. So what should c be? 2. So it's really, c should be 2. So I get 2 plus the sum, k equals 0 to infinity, negative 1 to the k, x to 2k plus 4 over 2k plus 1 factorial times 2k plus 4. And that's the answer. All right, I think we have to stop because our time is almost up. Good luck on the test. If this is not so bad, you won't think the test is so bad.